Ever wondered what a real competitive AI project looks like under the hood? I'm not talking about a single simple script, but a whole system that's built to win. Well, today, we're going to do just that. We're dissecting the anatomy of a top-tier machine learning code base to really understand the blueprint for success. Let's dive in.
Right off the bat, this one sentence from the project's own description tells you everything you need to know. This isn't about random experiments, it's about building a robust, repeatable machine. Every single part of the process, training, predicting, blending models, and submitting, is all part of a single engineered pipeline. That's the professional mindset we're going to explore.
All right, so here's how we're going to break this down. We've got 5 key parts. First, we'll look at the actual problem they were trying to solve. Then, we'll check out the code structure. After that, we'll climb what they call the experiment ladder, master the art of blending models, and finally, see what it takes to get across that finish line with confidence.
So, what's this all for anyway? Well, the whole project was built to tackle a classic problem from a Kaggle competition. It's a binary classification task. The goal? Predict if a customer at a Portuguese bank is going to say yes to a term deposit after getting a marketing call. It's a totally real-world business problem with a super clear objective.
Now, the task itself is pretty standard. The success metric, ROC, AUC, you've probably seen it before. But here's where it gets really interesting, the constraints. Look at this. No external data, no pre-trained models, and no AutoML. What does that mean? It means you can't just throw more data or a giant pre-built model at the problem. You have to win with clever feature engineering and a smart modeling strategy. That's it.
Yeah, with rules like that, your organization has to be on point. You can't just have a bunch of messy notebooks all over the place. This project is built on a solid foundation, a really clear blueprint that makes all that complex experimentation actually manageable.
And this, right here, this is the core workflow. These simple commands are basically the heartbeat of the whole project. You train something new, you test it out, you blend it with your other models, and then, and this is key, you run ablations. That's just a fancy word for tests where you take one piece out to see how important it was. It's this super disciplined cycle of build, test, learn, repeat.
Which brings us to a really cool idea. Improvement doesn't just happen in one giant leap, right? This project actually calls the journey an experiment ladder. Every new experiment is like another rung on that ladder, a step up from the last one, building on everything you've learned before.
So let's actually walk up that ladder for a second. It starts with something like Experiment 6, just searching for better model settings. Then, in Experiment 10, a whole new type of feature gets introduced. 12 locks in those gains. And then you get to something like Experiment 20, where they're using a sophisticated technique called adversarial weighting. It's a clever way to make the model pay more attention to the hard examples so it gets better at handling new, unseen data. See? Each step is a focused, smart improvement. And here's a perfect snapshot of that evolution. They didn't just start with the most complicated features they could think of. Nope. They started with a solid, standard baseline. It was only later, after tons of testing, that they started adding in these more sophisticated features to capture those really subtle patterns in the data. The model literally got smarter over time.
And you know, the search for a better model didn't just stop with one type of algorithm. Take a look at Experiment 24. They're testing out an MLP, which is a type of neural network. Now, the goal here wasn't necessarily to beat their main model. The goal was to find a different way of looking at the data. Having a diverse model like this is incredibly valuable when you get to the final blend. It just shows how thorough they were, leaving no stone unturned.
This brings us to one of my favorite techniques in all of machine learning, blending. The idea is so simple but so powerful. Instead of betting everything on just one model, you combine the predictions from several different ones. And what happens is, the team result is almost always stronger and more stable than any single star player.
The project uses this really smart technique called out-of-fold, or OOF-based blending. The simple version is, it's a way to test each model on data it has never seen during its training. By doing that, you can figure out the perfect recipe for mixing their predictions together. It's a totally data-driven way to get the best possible final result.
Okay, but that's the big question, isn't it? You've run dozens of these experiments, you've got all these models, you can't just toss them all into the mix and hope for the best. So how do you choose which ones actually get to be in the final blend?
Well, they have a system for that, and it is incredibly disciplined. A model only gets in if, 1, it's already a strong performer on its own, and 2, this is the secret sauce, its predictions are different from the other top models. You want high performance, yes, but you also want high diversity. And finally, the blend itself has to prove it's actually way better than just picking the single best model by itself. All right, so you've engineered your features, you've climbed the experiment ladder, you've crafted this beautiful blend. You're almost there, but the job isn't done yet. These final steps are all about pure discipline, validation, and tracking everything.
This might seem like a small thing, but trust me, it is absolutely critical. Every single time they create a file to submit, it first runs through a validation script. This little script just checks for simple stuff. Does it have the right columns, the right number of rows? Are the IDs correct? It's a safety net that prevents you from making a simple, silly mistake that could cost you everything.
And that discipline extends to tracking every single result. This is the project's leaderboard journal. Every submission is logged with a timestamp, which experiment it came from, its score, and some notes. This isn't just a boring log file. It's a rich data set for understanding exactly what's working and what's not.
And it all adds up to this, over 20 formal, named, and tracked experiments. That number, it doesn't just represent a ton of work. It represents a structured, intelligent process of discovery and constant improvement.
So, when you boil it all down, what's the big takeaway here? It's that a winning AI solution is rarely ever about finding one magic algorithm. It's about building a system made of clean, organized code, a disciplined process for experimenting, and a rock-solid method for tracking your results.
What we've just walked through is a blueprint for solving a really complex problem under some pretty tough constraints. It's a roadmap from raw data to a top-performing solution. So the question I'll leave you with is this: what problem in your world could you solve with a system just like this one?